The problem facing the statistician is to use the evidence in a randomly selected sample of data to decide whether to accept the null hypothesis, big H sub naught, or to reject it in favor of the alternative hypothesis, big H sub 1. If the null hypothesis is accepted, this does not mean that the statistician declares it to be true. Rather, it is accepted tentatively with the recognition that it might be rejected later based on additional evidence. For this reason, statistical hypothesis testing can be posed as either rejecting the null hypothesis or failing to do so. The p-value in any given sample, the sample average big Y bar will rarely be exactly equal to the hypothesized value big Y, the hypothesized value mu sub big Y naught. Differences between big Y bar and mu sub big Y naught can arise because the true mean in fact does not equal mu sub big Y naught. The null hypothesis is false, or because the true mean equals mu sub big Y naught. The null hypothesis is true, but big Y bar differs from mu sub big Y naught because of random sampling. It is impossible to distinguish between these two possibilities with certainty. Although a sample of data cannot provide conclusive evidence about the null hypothesis, it is possible to do a probabilistic calculation that permits testing the null hypothesis in a way that accounts for sampling uncertainty. This calculation involves using the data to compare the p-value of the null hypothesis. The p-value, also called the significance probability, is the probability of drawing a statistic at least as adverse to the null hypothesis as the one you actually computed in your sample. Assuming the null hypothesis is correct, and in the case at hand, the p-value is the probability of drawing big Y bar at least as far in the tails of its distribution under the null hypothesis as the sample average you actually computed. For example, suppose that in your sample of recent college graduates, the average wage is $22.64. The p-value is the probability of observing the value of big Y bar at least as different from $20, the population mean under the null hypothesis, as the observed value of $22.64 by pure random sampling variation, assuming that the null hypothesis is true. If this p-value is small, say 0.1%, then it is very likely that this sample would have been drawn if the null hypothesis is true. Thus, it is reasonable to conclude that the null hypothesis is not true. By contrast, if this p-value is large, let's say 40%, then it is quite likely that the observed sample average of $22.64 could have arisen just by random sampling variation if the null hypothesis is true. Accordingly, the evidence against the null hypothesis is weak in this probabilistic sense, and it is reasonable not to reject the null hypothesis.